Hey everyone, and welcome to The Explainer. Today, we're demystifying the actual engineering that bridges the physical and digital worlds, and that is sensor selection. Think about it. Sensors are literally the sensory organs of our modern machines. They're what translate the messy, chaotic physical world into the crisp, precise digital language of ones and zeros that our industrial systems can actually act upon.
Here is our roadmap for this explainer. We're going to cover 1. The basics of transducers. 2. Criteria for sensor selection. 3. Smart sensors and IoT. 4. Microsensors and MEMS. 5. Thermal and heat flux. And finally, 6. Environmental and gas sensors.
All right, let's jump right into Section 1, the basics of transducers.
So in professional instrumentation, a transducer is actually a lot more than just a basic sensor. It consists of the sensing element itself, plus the necessary signal conditioning circuits. Take a classic thermocouple measuring temperature, for instance. The raw signal it puts out is incredibly weak. The transducer packages that sensor with circuits to amplify and condition the signal, so it's actually strong enough for processing down the line.
Ultimately, these devices act as machine senses. They take a physical input, say the mechanical strain on a bridge, the intense heat of a furnace, or the pressure of a fluid, and convert it into a measurable electrical output, usually a voltage or a current. Without this fundamental conversion, industrial automation, robotics, and honestly even our everyday electronics simply wouldn't exist.
Moving right along to Section 2, Criteria for Sensor Selection.
If you're designing a system, this list right here is kind of your holy grail. Obviously, you have to consider the operating range, the useful range of the input quantity. But the absolutely crucial point here is the loading effect. This is such a fascinating engineering principle. Ideally, the sensor you select should extract absolutely zero energy or force from the quantity it's measuring. I mean, if your sensor inadvertently changes the temperature of the water it's trying to measure just by being there, well, your data is already flawed. You also have to factor in environmental stability, how well it holds up against vibrations, wild temperature swings, and electromagnetic fields.
Drilling down into the electrical aspects for a second, output impedance is massive. While zero output impedance is physically impossible, engineers need it to be as low as humanly possible. Why? Because it directly determines how much power can be successfully transferred to the succeeding stages of your instrumentation system without degrading the signal. Furthermore, while high accuracy is great for reducing how often you need to calibrate the device, in a lot of industrial applications, high repeatability is actually considered even more critical than absolute accuracy.
Okay, let's get into Section 3, Smart Sensors and IoT.
So, smart sensors don't just passively send raw voltage down a wire anymore. They're actually processing data right at the source. And the advantages are striking. They offer incredible energy efficiency, they filter out erroneous noise before even sending the data, and their built-in analytics severely reduce the need for heavy external processing. But, and it's a big but, connecting physical sensors to digital networks introduces a major disadvantage: susceptibility to tampering and hacking. When a sensor is smart enough to talk to a network, well, a network is smart enough to talk back, creating some real cyber vulnerabilities.
Despite those risks, though, they are for sure the driving force behind Industry 4.0. Factories use smart temperature and vibration sensors for real-time diagnostics, basically catching a machine before it vibrates loose or overheats. In the security sector, network thermal imaging sensors detect body heat and communicate instantly with smart locks and alarms to create this comprehensive, fully automated security picture.
Let's zoom way in for Section 4, Microsensors and MEMS.
Looking at the architecture of a MEMS pressure sensor, the sensing element is a thin silicon die, and we're talking sometimes just micrometers square. Using microfabrication techniques, a cavity is etched right into the silicon, leaving this microscopic, super thin top surface that acts as a diaphragm. When fluid or gas pressure is applied through that inlet, this tiny little silicon diaphragm physically deforms.
Now, to measure that microscopic deformation, engineers implant tiny components called piezoresistors, labeled R1 through R4, right beneath the surface of the silicon die. You can think of these as miniaturized strain gauges. Because of the piezoresistive effect in the silicon, when the diaphragm bends under pressure, the physical dimensions of these resistors change, which directly and instantly changes their electrical resistance.
To translate that resistance change into something a computer can actually read, those piezoresistors are wired into a classic Wheatstone bridge circuit.
As the pressure stretches some of the resistors and compresses the others, the bridge becomes unbalanced and it outputs a precise voltage that is directly proportional to the physical pressure applied to that microscopic diaphragm. It is just a stunning piece of engineering, perfectly bridging the physical and the digital.
Because they are so unbelievably small and reliable, MEMS sensors are literally everywhere. In the automotive industry, MOEMS-based accelerometers and pressure sensors are the hidden brains behind stability control, active suspension, and adaptive cruise control. In robotics, they enable incredibly precise micromanipulation, allowing machines to interact with their environment on a microscopic scale safely and accurately.
Moving on to Section 5, Thermal and Heat Flux.
A standard temperature sensor just tells you how hot something is, but a heat flux sensor is much more dynamic. It measures the actual rate of thermal energy transfer across a surface, expressed in watts per square meter. Whether the heat is convective, conductive, or radiative, these transducers use specific geometries, like a Garden gauge or a Schmidt-Belliter gauge, to monitor the sheer intensity of the heat flow.
Notice how the heat flow in a flat-plate heat flux sensor travels exactly perpendicular to the surface. It moves straight through the filling material from the hot side to the cold side. The temperature difference across that material is what generates the electrical signal, usually relying on an arrangement of metals like copper and constant tan to make the magic happen.
Typically, these sensors use a thermopile, which is simply a bunch of thermocouples connected in series. When selecting a heat flux sensor, engineers absolutely love thermopiles for their brilliant stability and their low ohmic value, meaning they don't pick up much electromagnetic interference. That gives you a great signal-to-noise ratio. Also, zero input perfectly equals zero output. But the critical trade-off? Well, they suffer from low sensitivity. So if you're trying to measure incredibly subtle heat transfers, this might not be your best option. Finally, let's wrap up with Section 6, Environmental and Gas Sensors.
If you want to measure chemical compositions, like finding carbon monoxide in a room, you generally have two primary choices. Semiconductor gas sensors actually change their physical resistance when a gas interacts with their surface. They are compact, cheap, and respond very rapidly, which makes them perfect for a home air quality monitor. But they're fragile and super sensitive to humidity. On the flip side, optical sensors analyze how light interacts with pollutants. They are incredibly accurate and reliable over the long term, but they're far bulkier and much more expensive. So your selection depends entirely on your budget and your required precision.
We see this exact selection dynamic in water quality measurement too, specifically with total organic carbon, or TOC. If a facility just needs general, real-time process monitoring for their own internal information, a standard TOC sensor does the job perfectly. But if that data is going to be used for strict regulatory reporting or critical quality control, the standard sensor just isn't going to cut it. The facility must select a full TOC analyzer, prioritizing absolute instrument accuracy above literally all other characteristics.
And that brings us to the end of our explainer. We've seen how transducers convert physical reality into electrical signals, explored the strict criteria engineers use to pick the perfect device, and looked at real-world applications from microscopic MEMS to smart environmental monitors. So I'll leave you with this to think about. As our world becomes increasingly automated and as physical and digital systems continue to merge, which sensor technology will you be relying on next to bridge that divide? Keep observing the world around you, because a sensor somewhere is definitely observing it with you. Thanks so much for joining me on The Explainer.